All right, we're going to look at the hypotenuse leg right triangle congruence theorem, and this could be abbreviated the HL theorem. We are going to start with our givens of two right triangles, and we're going to prove that they are congruent. So given a right triangle with a leg and a hypotenuse being corresponding congruent to some other right triangle where we know the same measures, we are going to prove this theorem. Now, one thing you might think is that there's already enough information to know they're congruent because we have side-side angle. But if you remember, side-side angle is the one that doesn't work for proving congruence because there could be more than one triangle that has the same side-side angle and not be a congruent triangle. So we have to take a different approach. So let's go ahead and get a hold of what we know and then try to work with finding the rest of the pieces. So we're going to go ahead and label our triangles so that we can talk about them. So my first one I'm going to call ABC. So I'm moving from the narrow angle towards the right angle. So this one I will do X, Y, and Z. And so I move again from the narrow angle towards the right angle. And so we're going to try to prove these. So given is segment AB is congruent to segment XY. So that's a given. We also have that the hypotenuse is congruent. Again, that's given. And we also know that angle B and angle Y are going to be congruent. So those are all our givens. So this statement here talks about corresponding congruent parts. And so these are our congruences with corresponding pieces or parts. So now what can we do? Well, it would be great to be able to make a statement about this side or one of these angles. And we do have something that we can use with right triangles and sides, and that is the Pythagorean Theorem. And so let's make a statement about the Pythagorean Theorem. Looking at this top triangle, or this side squared plus this side squared equals this side squared. So that's the Pythagorean Theorem. Let's make that statement. So we have the Pythagorean Theorem with this statement. You may not be familiar with the notation like this, but we are talking about this side squared, so we're showing that that segment in parentheses is squared. And so this is just the Pythagorean Theorem that you should have learned in the past, but slightly different notation to fit the geometry that we're working with. If I have these statements about things added together equaling other things and they're squared, I need to find some way to convert our givens into something usable in this form. So for instance, let's take a look at this. So we have the ZX side here, we have the ZX side here. So I'm going to take this given here and we're going to do some changes to it so that it fits in with this pattern. So the first thing I'm going to do is I'm going to take this line and I'm going to say that AC is equal to XZ, and we can switch from the congruence statement to the equality statement with the definition of congruence. And then I'm going to square each side. And we're going to do that by definition of squaring. So now I have a statement here. And if I wanted to at this point, I could substitute AC squared into here and have a true statement, because I've shown where I can move from our givens to have some form that fits in with this Pythagorean theorem. I've only worked with one triangle though, and now I want to work with a second triangle and do the same thing. I want to set up the Pythagorean theorem. So I'm going to set up AC squared, or AB squared, and I'm going to add it to BC squared. And that's going to equal AC squared. It's Pythagorean theorem again. And do you see I have an AC squared statement here, an AC squared statement here, an XZ statement here, and an XZ statement here. Since these are equal and these terms appear in both, by transitivity I can set them equal to each other. So that's what I'm going to do next. So I have this statement here. So now there's something else that I haven't used yet. I've got this other statement that AB is congruent to XY, and by the same argument that I used here, taking the second statement from the given, switching it into something that's squared and equal, I can use this as a substitution into here so that I have an AB squared on both sides of this statement here. So that's what I'm going to do next. All right, so I have gone through those three steps all over again, and I've substituted the AB in for the XY. And so at this point, I can subtract AB squared from both sides and have that YZ squared is equal to BC squared. So YZ is this extra side here that we didn't have a congruence mark on yet. BC is this side here that we didn't have a congruence mark yet. So we are almost to the point that we would like to be at. So we're going to subtract AB squared from both sides. So we've got this statement. Now we're going to take the square root of both sides. Call that the definition of square root. And so I have that YZ is equal to BC. By definition of congruence, they're congruent to each other as well. And now at this point, I have where I can say that this is congruent to this, and so this triangle has to be congruent to this triangle by side, side, side postulate. And so that's going to be our last statement here. That triangle ABC is congruent to triangle XYZ. All right, so you can see the final steps here. We are done with this proof, and we have proven this theorem. There are three other possible proofs that you could do dealing with right triangles and different variations of angles and sides. Go ahead and take a look at that and see what you can do with those. Cheerful calculations.